I know the transport equation theory is a little bit hairy and uses a lot of functional analysis. So before I continue with this, I would maybe do a step back and compare what I've done so far to the one-dimensional case. Because I think the one-dimensional case is easy to understand and we can be quite comfortable with this. And so let's maybe compare the general transport equation to the 1D case. And I'm sure this will make many things very clear. So the 1D model was this. U plus t plus gamma u plus x equals minus mu u plus mu over 2 u plus u minus, and u minus t minus gamma u minus x is minus mu u minus plus mu half u plus u minus. Right, and then I use kind of the second notation for the system because I said this is the kind of the analog. So in n dimensions we have like following. nd, we have p of txv time derivative plus v times gradient p txv equals minus mu p of txv plus mu integral t vv prime p of tx v prime dv prime. So what I like to do now is to understand the 1D case as a special case of the general case. So let's do that. So the first question is, what is V? So okay, first. So now in 1D, so what is V in this case? And you are invited to help me to figure all this out. So V was a set of possible velocities. So what is V in this case, in the 1D case? So how many velocities do we have in the 1D equation? 2, right? One going right, one going left. So, and the speed is gamma, so then the velocities is minus gamma and plus gamma. Okay? So then the set V is just 2 elements, plus minus gamma. So meaning, if you look here already, then this integral is really just a sum over 2 elements, right? So the integral is just a sum of 2 elements. But I come to this later. Then first u plus of t and x is then of course p of t and x and plus gamma, right? And then u minus of t and x is p of t and x and minus gamma. So meaning for each velocity here, you have one of these p's. So meaning in the general case, this is not one equation, it is an infinite system of equations. Right, for each v in the set capital V, we have this equation here, but they're all coupled together. Okay, so then our Banach space which we are working in is now R2. So typical elements are then u plus of tx and u minus of tx. In the general case, we have L2 over the velocity space, but now the velocity space is discrete. So I can use the 2 norm on R2, but I can use any other norm because they're equivalent. So these are the elements we are looking at. Time and space in this case are just parameters. So it's really only about the velocity dependence. So it's R2. Then the kernel, the integral kernel, T. This tells you the probability of jumping from V prime to V. Now, in this model here, we see that the probability of jumping from plus to plus is 1/2, and from jumping to minus to plus is 1/2, etc. So in this case, the kernel is just 1/2. That's it. Okay? So just a constant number. Now let's look at the this turning operator, T. So that's an operator now from the Banach space to the Banach space, R2 to R2. And I said this here is T without the mu. So this is a curly T. So now we have to do this integration. And I said the integration now is a sum over 2 velocities over plus and minus. So then we have whatever T is. So T is 1/2 times u plus 1/2 times u minus. Okay, So then this t is a vector. It has two components. It is 1/2 u plus u minus, and 1/2 u plus u minus. So that, and then this is exactly this term here, right? These two terms with the factor mu. So the mu was not in the definition of t, but this is the integral operator. But then it's a linear operator in u plus u minus, so you can write it in a matrix form. So then this is 1/2, 1/2, 1/2, 1/2 times u plus u minus. Okay, and then I was interested in the spectrum of this matrix. So in the general theory, I was looking at the spectrum of t, of this integral operator. Now it's a matrix, so it's easy to talk about eigenvalues and so on. So this guy has eigenvalues. Lambda 1 is equal to 1, and lambda 2 is equal to 0, I think. Let's see. Yeah. Yeah, 0, it must be 0 because it's not a full rank matrix, and then it has an eigenvalue 1. And what is the eigenfunction? The eigenvector. So if I have this matrix 1/2, 1/2, 1/2, 1/2, and I multiply with 1, 1, yeah, then I get 1, 1. So 1, 1 is now what earlier was the function constant in 1. So now it's a vector which has 1 as entries. And it has the eigenvalue 1, and it is the leading eigenvector. And this was the result of Krasnodębski, that we have a unique leading eigenvalue and a eigenvector belonging to it. And so this is the vector 1, 1 in this case. So 1, 1 is what I called phi 0 in my theory. So then what else? And then we have L. So today I will talk about this operator, and this I call L, so taking everything together. And meaning in the 1D case it would be this. So taking all this together. So then we have L is also a map from R2 to R2. And then L of u plus u minus is the full right hand side. So it's minus mu u plus mu half u plus u minus, and minus mu u minus plus mu half u plus u minus. And now I'm interested in the eigenvalue and eigenvectors of L, but this is equally simple. So again, we can write this as a matrix, and this turns out to be this one, minus mu half mu half, and minus mu half times u plus and u minus. And now if I take the eigenvector from before, this phi 0, which is 1, 1, if I now multiply with 1, 1, then I get 0. Okay. So then here we find L of 1, 1 is 0 times 1, 1. So then this phi 0 is still an eigenvector, but now the eigenvalue has become 0. Okay. So lambda 0 is 0, phi 0 is 1, 1. And then we have another eigenvalue. What is the other one? So the second one, lambda 2, is minus mu. And then the eigenvector we can compute, but it is not important. It's only important that it is not a positive vector. So then we have this. What else do I need? And then I need the kernel of L. So it is the null space of L. So it is the vector space which is mapped to 0. Okay, and so the kernel is then the span of 1, 1, or I write it like this as well. So the vector space spanned by this vector 1, 1. Now just for notation, so do you use this KER to denote the kernel of an operator, or do you write it in a different way? So you have seen that? Okay. And then for the span, so do you use this symbol for a span as well? Okay, great. So then we are on the same page. So in the general theory, I studied T. So we were kind of here with the phi 0. And I haven't done the general theory for this L yet. So that would be the next steps to find the properties of L. In the 1D case, we have it done now. We have an eigenvalue 0. We have another eigenvalue negative. We have an eigenvector 1, 1. And we know what the kernel of this operator is. So this is now what I like to do for the general case also. So feel free to ask questions if you want to. So in the general case, we define L of P of V to be minus mu P of V plus mu, and then the integral operator is the curly T. So the T applied to P of V. And again, we need the adjoint just because it's so much fun to take them both. So minus mu P of V plus mu T star P of V. Okay. And now we know the spectrum of T and of T star, so it is not so difficult to find the spectrum of L and L star. So first of all, you multiply with the factor of mu here, and then here you have basically the identity matrix which you add. It's the identity map. So we get the following with lemma 4. So assume T1 to T4, then 0 is a simple leading eigenvalue. Of both L star and L with leading eigenfunction phi 0 is equal to 1. Okay, so the same as we found here, we have an eigenvalue 0. The eigenfunction here is 1, 1. In the general case, it is the constant function 1. And then all other eigenvalues satisfy minus 2 mu is less or equal real part of lambda is less than 0. So we can bound the real part of all other eigenvalues away from 0. They're all negative, but they're not too negative. They're bounded by minus 2 mu. So here we got the other one was minus mu. So it's right in the middle of that interval. In the general case, we can have a little bit more negative. And then also all other eigenfunctions have mass 0. Mass equal to 0. So let's do a little proof of this. Many of it follows directly from the Krasnodębski theorem, which I have shown yesterday. So T and T star have spectral radius 1. So if I multiply this as mu T and mu T star, then they have spectral radius mu. Okay. And then 1 is the leading eigenvalue here, so mu is the leading eigenvalue here. And so this means that then minus 2 mu is the lower bound of all the real parts of the eigenvalues less than 0, because we are shifting with another minus mu, so we can get a minus mu from here and a minus mu from here, so we get minus 2 mu as the maximum size of the eigenvalues. So that's the lower bound. For L is minus mu phi plus mu t phi. Okay. And that phi 0 is an eigenfunction is easy to check. We just plug it in and we get the eigenvalue 0 for this. So easy to check that L at phi 0 is actually 0. Do I want to write this down? Yeah, let's write this down. That helps. So meaning L phi 0 is minus mu times the one function plus mu integral t v prime 1 d v prime, which one? V prime. Right. And now I use the condition T4. So now the last condition, I wrote them down here again. These are our conditions. The last condition says if I integrate over V prime, I get 1. So then this integral is 1. And then I have minus mu plus mu, so I get 0. And then 0 times the one function comes out of this. Okay, so that is straightforward. And now you see that I need a condition T4, because otherwise this would be false. Okay. So then the mass thing. So consider another eigenfunction. So let phi 1 be another eigenfunction. Well then, phi 1 must be orthogonal to phi 0. Yeah, so phi 0 was a unique leading eigenvector, eigenfunction. So any other eigenfunctions are orthogonal. And so then the mass phi 1 of v dv integral, yeah, is the same as integral of phi 1 v times phi 0 of v dv, which is 0 by orthogonality. Okay, phi 0 is equal to 1, so nothing happened. So then the mass of these other eigenfunctions is 0. Okay. So that's the proof of this. All right. Now there's one property which follows from T3. Let's look at T3. What do I want? Okay, I want to give you an argument why this condition T3, so that this norm of curly T on this subspace 1 orthogonal is less than 1. I want to show you where this plays a role. So we consider a function psi in 1 orthogonal, and then we are looking at the integral psi L psi dv. So I take psi, I apply L, and then I multiply with psi and integrate. So that's a term which will show up later. Now if I do this, this is minus mu integral psi square dv plus mu integral psi t psi dv. Okay, so I just use the definition of the operator L and sub in those two terms. But then I can estimate this, the second term, I can estimate this by the operator norm of t. Okay, so then I get this is less or equal minus mu integral psi square dv plus the operator norm of t in the orthogonal subspace times integral psi square dv, and I must need a mu here in the front. So that's basically a definition of an operator norm, that I can do this. This up a little bit. So then this can be written as minus mu 1 minus the operator norm, 1 orthogonal, times the integral psi square dv. Okay, so I put this operator norm of t with a minus sign into the bracket, and then there's a minus sign in front, so together this makes a plus sign. And now this coefficient I give another name. I call this mu2, and this is less than 0. And this is only less than 0 if the norm of t is less than 1. And this is what I assumed in T3. So, by assumption T3, we find mu2, which is minus mu 1 minus norm of t in the orthogonal complement, is less than 0. And this is another condition which I need. Actually, what this is, if I do the diffusion limit, then this is the parabolicity, or this is the uniform ellipticity. So if you compute the ellipticity constant of your parabolic limit later, then this mu2 will show up, and this will show you that you have a parabolic limit indeed. So that's why this is important. Okay. Yeah, so I know this is all very function analytic. It will get better, but before it gets better, it gets worse. So we have a little way to go. Yeah.
So why P and T star have a spectral this one? So where does it come from?
So this one here, this was the Krasnozelsky we just did last lecture. Krasnozelsky. So that is, I just did it last lecture. So maybe just look back in your notes. So that was this complicated theorem of Krasnozelsky. Okay, so I would like to go and make an example, another example, which really helps to understand. But I need one more notion, and this is the notion of normal operators. So let's maybe do that here. Normal operators. So let's think about matrices first. So who has heard about normal matrices? Okay, a few of you. So who does know what a normal matrix is? It is not used so often. Usually you know it when you take linear algebra, you know it quite well. But then 2 years later you forget everything. So, so who knows what a normal operator is? Yeah.
A star equals A star A.
Yeah, that's right, exactly. So are you teaching linear algebra right now? Right, so that's right. So A star equals A star A. Right, so it is a little bit weaker than self-adjoint. So if something is self-adjoint, it would satisfy this, of course. If something is symmetric, it would satisfy this. But it's just a commutation between A and A star. And it turns out that this normality helps us a whole lot to deal with these conditions T1, T2, T3, and T4. So let me show you how this works. So there's a theorem 5. Theorem 5 is a classical result which just says that we can have a spectral decomposition if we have a normal operator in a Banach space. So if A is normal, then there exists a complete set of orthogonal eigenfunctions. So a complete of orthogonal eigenfunctions. And A has a spectral representation of A can be written as a sum lambda j pj, where lambda j are the eigenvalues of A and pj are the spectral projections onto the corresponding eigenspaces. I'm sure you have seen this somewhere, at least for matrices. yeah, so lambda j are the eigenvalues, pj are the projections to the eigenspace. Okay. All right, and then we can choose the eigenvectors, of course, to be normalized to be equal to 1. So I call them phi n, so phi n are these eigenvectors. So then how do we use this? Lemma 6. So if t is normal, then T3 follows from T1 and T2. T1 and T2. So let me show you the conditions again, which we had. So if you just look at T3, it looks a little bit hairy, right? You have an operator, you have to restrict it to a subspace, and then find the operator norm, and this has to be less than 1. So to me it looks like a little bit complicated to do. But if we know that T is normal according to the lemma, then it's enough to check T1 and T2. And then T3 follows for free. So that's really cool. That's a really cool thing. And this is indeed a criterion which we can use later in our examples. So yeah, let me prove this. Yeah, so we want to show that T3 follows, so we want to estimate this norm of the operator T. We are assuming T1 and T2 is correct. So let's just start with this norm, which we are interested to compute. 1 orthogonal. Okay. So let's use a definition of the operator norm. So then this is the supremum over all functions in this subspace, 1 orthogonal, which are normed to be equal to 1. And then apply the operator to this function, and then look at the 2 norm. So we are working in L2 related to velocities. Okay. But then we have the spectral representation, so we can write this to be the supremum over phi, the norm of T applied to the sum of n is 1 to infinity, alpha n phi n in the 2 norm. And here I'm very specific. The first eigenfunction is phi 0, right? So phi 0 is equal to 1. We know that already. So I start my sum excluding this bit. Okay, so I start my sum only with the higher order eigenfunctions. And I can do this because I'm in the orthogonal complement of 1. Okay? So I'm excluding 0 from this here. So then I apply the linear operator onto the sum. N is 1 to infinity. And then I get my eigenvalues, lambda n, phi n, in the 2 norm. Okay. But then I know by Krasnozelsky that all these lambda n's have a real part less than 1, or actually the spectral radius is bounded away from 1. So I can write this as sup over all these phi of sum n is 1 to infinity alpha n lambda n square to the 1/2. Oh yeah. So if you have a spectral representation of your functions, you can write the L2 norm in this way. Okay, so it's just the coefficients, and then I use the fact that the lambdas are less than 1. So this is less than supremum phi of the sum n is 1 to infinity alpha n square. But then the sum of the coefficients of the original function is just the L2 norm of the original function. So this is phi in the 2 norm, and then this was equal to 1 as we have started. Okay, so and then we got an inequality sign here, so making this norm, which I'm interested in, really less than 1. Okay, and what I used the Krasnodębski theorem, and I used the spectral representation, so which is T1, T2, and the normality of this operator. Cool. So in our case, so when is this the case? When is T normal? This integral operator, when is this normal? So let's compute this out. So let's compute T star applied to a function phi. So then this, whichever way you want it, so maybe you apply T star first. So then those would be T applied to the integral T of v prime v phi of v prime dv prime. Okay, so that's a new function of v, and then we apply this integral operator to this new function of v. And so then this is a double integral of T v and v double prime T v prime v double prime, yeah, that's a double prime now, phi of v prime dv prime dv double prime. So it's really a bit tedious. You need to sit down and carefully understand where a prime and where double prime comes, so that you have the right order of these terms here. Okay. So and the opposite one, T stars T phi. Yeah, you can do the same game for T star T, integrate over the first and the second later, and you have no idea how often I got confused doing this. So it is one has to sit down and do it carefully. So then here we get T v double prime comma v times T v double prime comma v prime phi of v prime dv prime dv double prime. So, but now we can compare the kernels. So now we have kind of a double integration kernel, and they have to be the same for it to be normal. So this means we find something like integral v T of v double prime T of v prime v double prime dv double prime must be the same as the integral T of v double prime v T of v double prime v prime dv double prime. So that's just what it is. But it's a cool condition. So if I give you a T in a few moments, we can just check. We put it in and we check is it right or not. So it's an easy criteria. So let's do two examples where we check all these conditions now. So the first one is called the Pearson Walk, or Hans Osmer calls it the bakery walk. So for example, in France or in Germany, you have wonderful bakeries where they bake all kind of good stuff. And so if you're hungry in the afternoon, you just go out of your office and you hold your nose in the wind, and then you smell a bakery on the next corner, and then that's where you go. So so it's kind of a directed bakery walk. And it's kind of chemotaxis. But actually, in this case, I don't want to do chemotaxis. Maybe this is too early here. So I do simpler. So v is s times Sn minus 1. So meaning any direction, but with the speed s, fixed speed. Okay. And then the directional kernel is just constant. So we have equal probability to switch from any two velocities from one to the other. The probability of doing this switch is always the same. 1 over the size of v. You can compute the size of v. If s is two-dimensional, then you have the outside of the sphere, which comes in there. So this is size of v can be computed in any dimension. So let's check our conditions for this. So I don't know. I think let's see. So I think I want to give this as a little exercise for you guys. So again, take a piece of paper and check all the 4 conditions, T1, T2, T3, T4 for this case. And of course use the normality if you can. So maybe that helps you. So now I got something on here. Or was it there all the time? I don't know. Screen on. Screen off. Oh, whatever. It doesn't matter. Okay, so check conditions T1. So who thinks T1 is correct? Just raise your hand. Yeah, T1 is simple, right? You just these two integrals and it's non-negative, so T1 is okay. T2. So who thinks T2 is correct? Okay, so has a simple argument. So why is T2 correct? What did you do?
Just usually is same as T. I think it's okay.
Okay, so say this again. So how did you prove T2? Okay, so then the best way is just 1 over v is positive, right? So this c is actually vv prime. It's strictly positive. So strictly positive is the strongest we can have. So then it's certainly u0 positive. And the adjoint also. So this implies T2. And then T3. So is this true? Who thinks T3 is true? You can still raise your hand. I will not ask you to answer. So it's correct because of normality, right? So T is actually symmetric. It is self-adjoint, it is normal, it's all those things. So then from T1 and T2, T3 follows. T is normal. And then T4 is also fine. You just integrate over the v prime variable and you get 1. So that's an example where everything works out fine. That's good. So let's do another example. And this is movement on a fiber network. Movement on fiber network. And this is basically the model which I will use later for the brain tumors, for example. So the idea is you have given some fibers in the background, so it could be nerve fibers in the brain, for example. And then it is known that cells kind of attach to these, but they also follow these fibers. And then move along this direction, say. Okay? So then there's a preferred direction. If a cell now comes from here, so let's have some other cell, it comes from here, then it will turn in this direction. So then the turning distribution T is no longer uniform, it is very biased. You have a preference to go this way, or in this example you could also go the opposite way. But you certainly would like to align with the nerve fibers. So let's call theta a unit vector and Sn minus 1. And I denote the direction of fibers by a function q of x and theta. So this q is a distribution of fiber directions. It's a distribution of direction theta, and at each location x I might have a different distribution of these. So then the integral, or Sn minus 1 q of x and theta d theta is equal to 1. Okay, so it's also probability density for directions. All right. So then I also simplify a little bit. I say actually v is Sn minus 1. So I normalize the speed to be equal to 1. If I don't do this, I just have to carry a scaling factor around all the time. So let's forget about that for now. So v is just the shell. All right. And then I set t of v prime is equal to q of q of x and v. So now the transitional probability to switch from v prime to v depends only on the fiber direction, and I choose a direction which is given from the fiber network. And I choose a direction v with this probability, with the probability q. So for example, if I have like 5 fibers going this way and 1 fiber this way, and a cell comes from here, then it will switch 5 times in the direction of the 5 fibers and only once or 1/5 in the other directions. So that's what I have. So t is this, v is this. And we can again check our conditions T1, T2, T3 and T4. But this time let's do it together because this is a bit more complicated. Okay, so T1, so Q is positive, non-negative, so that's fine. Integral of T v prime dv. This is integral of Q of v dv, which is equal to 1. So now I forget about the x dependence, so Q depends on x, but these properties really only relate to the v dependence, so I don't need to write down the x dependence here. So that's all good. Integral q square v dv dv prime. This is the size of v times integral q square of v dv. And so this is bounded for q in L2, Sn minus 1. So we need another assumption. We need to assume q is in L2. But this doesn't seem to be very restrictive. So we assume q is in L2. Then this is all good. Now T2. What did I write here? Yeah, so here we really need to check the U0 positivity for the iterates of Q. I'm sorry, but we have to do that. So let's maybe write down the iterates first. So what is T to the n of v prime v? So that is by definition an integral, many integrals, of q of v prime, q of w1, and so on, q of wn minus 1, of d w1 to dwn minus 1. Okay. And now the w integrations, they all integrate to 1. So q has the integral to be 1. So the inner w, q only depends on one variable, so I can integrate them one after the other after the other. They all integrate to 1. The only thing I keep is this guy. So this is q of v prime. And then similar for the other case, t to the n v prime v prime. This is then q to the q of v. So the iterates actually give us Q as well. So there's this is kind of cool. So we don't need to worry about higher order iterations in this case. So then if we want to check T2a, we have that this function u0v should be less or equal q of v prime, which should be less or equal rho u0 of v. T2b says u0 of v should be less or equal q of v, less or equal rho u0 of v. So which condition is weaker? Which condition gives us more freedom for the choice of Q? So I said earlier we need only one of these. We can actually choose which we think is easier for us to satisfy. So in the first case you have different arguments. This depends on V, this on V prime, this on V. So this basically means Q must be uniformly bounded. So it must be actually bigger than the maximum here and smaller than the minimum here. Okay? So this implies that the max of u0v is still less than q v prime, still less than the minimum of rho times u0 of v. So that seems to be very restrictive. This condition means that Q is U0 positive in the sense of Krasnodelsky. So this seems to be weaker. So Q of V is U0 positive. That's what it says. So we get another condition.
The first is the right side is less stronger than the left side.
Excuse me?
The right side of the that's just a lot stronger than the other.
Yes, but it's implied because you have a different variable v prime here. So
but this way is the same way.
Yeah. But you can always choose a v so that this is the maximum here, and then q of v prime must be always bigger than than this maximum for all v prime. No?
So if you can choose the V1 left hand side, V2 right hand side, if they can choose independently.
I see. Okay.
Then
Yeah.
you get that.
Yeah. Okay. So you cannot. All right. So then, don't forget about this.
Yeah, but that's very strong. That's very strong.
But it's still a strong condition. Yeah. Okay. Thank you. Good. All right. So that is this guy. Right, so then let's assume Q of V is U0 positive, so that doesn't seem to be very restrictive either. So what else do we have? Oh, here's a normality condition, so let's check that. So T3 is Q normal. Yeah. So we need to check those two integrations here. Okay, so now Q only depends on the first variable, but it does not depend on the second. So the left-hand side would be integral V, Q of V and Q of V prime, but then integrated on dV double prime. Okay, and the right-hand side would be integral V of Q V double prime, Q V double prime, dV double prime. So that's a funny relation. So what you get, this is an integration on V double prime. So this is the size of V times Q of V times Q of V prime. And then the right hand side you integrate over a Q square basically. So this is a number, so constant. So then you get that Q multiplied must be a constant. And on the left-hand side we have functions, on the right-hand side we have constants. So this is only the case if Q is constant. So it doesn't work. So only if Q is constant And of course we can choose Q as constant, but then we are back in the Pearson case, in the Pearson Walk, which we checked before. So we don't want this. So that's not good. Yeah.
What is U0 in this case?
What is U0? You can choose a U0. You can choose a non-negative function in the cone and then put it there. So U0 is a very good question. What is U0? So U0 can be anything you want, but it cannot be a zero function. So it must be a positive function. So for example, the simplest choice is so often you can choose U0 to be maybe 1/2 Q or something. If Q is in the positive cone, so then this would already work. Okay. So yeah, this is interesting. So let's need the last 5 minutes. That works. Here we got this. So we found it is not normal, so we cannot use the result T1, T2 implies T3, so we might have to check T3 directly. So there's still hope T3 could be satisfied, so let's check it directly. So we need to compute the norm of the operator and the orthogonal complement of 1. So let's write down what this is. This is supremum over all phi in the orthogonal complement, having norm equal to 1 of the integral q of v phi of v prime and dv prime. Okay, and but now we are lucky. So the q depends on v and phi depends on v prime, so we can take out q. So then this is the supremum over phi q of v times the integral phi v prime dv prime. But phi is in the orthogonal complement of 1, and we have seen that earlier that these functions have mass equal to 0. So if you integrate this, basically you write 1 times phi, and so then this is orthogonal, so this is equal to 0. So then the whole thing is 0. So basically the operator T restricted to the orthogonal complement is a 0 operator. So that's rather cool. So, and it certainly satisfies T3, so the 0 is certainly less than 1, but it turns out that this is actually really bad. It's not a good property. So, okay, so T3 is okay, but but T restricted to the space 1 orthogonal is the 0 operator, and this will not help us later when we do the limit. So that is problematic. Okay. So then the last condition T4. So then we have the integral of T of v v prime dv prime. So that's integral q of v dv prime, which is q of v times the size of capital V, which is supposed to be equal to 1. And now this only works if q is a constant 1 over v. So only true for Pearson Walk, only true for Pearson Walk. Otherwise it's not true, and then here you see one example where T4 fails. So for the interesting case like brain tumors, T4 would fail, and we have to do something else. So otherwise T4 is false. So what we find for this case, T4 doesn't work. T3 is problematic. We get a 0 there, which is something I don't like. And so then we will see later in later lectures that we have to do a little bit different theory for this case. But then in the afternoon, I will continue with the good case. So when we still have T1, T2, T3, T4, and then I will finally be able to talk about the parabolic limit. And then we do it for the Pearson Walk as an example to see how it works. All right, so that's it. Lunchtime for now. Thank you.